people use accuracy, lay people use accuracy all the time. So I think that makes a lot of sense to focus on for a machine learning level 1 course, as well as in this episode so far. But I understand that you would like to fill us in on some slightly more sophisticated metrics.
Yes, which is the R squared. So indeed, for classification, evaluating model is super intuitive to understand. The model makes predictions. If it's binary classification, 0, 1. And the accuracy will simply be the number of correct predictions divided by the total number of observations in a test set. So that's fine. However, for regression, it's not that intuitive to understand, simply because what you have to predict is a numerical continuous number. And therefore, there is no such thing as the number of correct predictions. Usually the prediction will always be incorrect. So it's more like you will see how close the prediction is to the real result to assess whether that prediction is rather correct or incorrect. The closer it is to the real result, the more correct it will be. And therefore, there is no such thing as the accuracy for regression. And instead, we have the R squared. And so the R squared is indeed an evaluation metric for regression models that will take values between 0 and 1. And the closer the R squared will be to 1, the more accurate, but we should not say accurate, the better predictions will give your regression model.
Cool. Makes perfect sense. And then I also know that there's something called adjusted R squared. What's that all about?
Love it, John. So adjusted R squared is a metric that it's better to use adjusted R squared to avoid a certain pitfall of a multiple linear regression, where in a multiple linear regression, you can add more coefficients and more independent variables. As you add more independent variables and coefficients, what happens to the normal R squared, without going into the math. So of course, we explain this a bit more detail in the course and the reasoning behind this, but in just kind of like intuitive or high level sense, why it's dangerous to use just the normal R squared is because as you add more independent variables to your models and more coefficients with them, what can happen is your model can just disregard independent variables that don't make any improvement to the model, but it can take any independent variables that make a tiny, slightly improvement to the model, and the formula to R squared is such that it won't get worse. Like the model has like a trick; it can cheat the system and can just zero out any new independent variables that will make the R squared worse, and it can accept tons and tons of independent variables, especially if you have a problem where you have lots of features that you could be using, you don't know which ones to use, and you just keep adding them. Then through some random chance correlations, your R squared will be getting better, and you'll end up with a model of hundreds of independent variables that actually don't mean anything, but because of the way that R squared is structured, the model has accepted them. So that's why adjusted R squared was introduced, and that's what we want to share on this podcast. Like the takeaway from this point that we're sharing in the podcast is that the difference between R squared and adjusted R squared is that adjusted R squared penalizes your multiple linear regression model for having extra variables, extra independent variables. And so that means that the variable has to actually make a good enough impact, has to adds enough value to the model that is greater than the penalty that your model is getting in order for that variable to be accepted. So it's a way of building models with a reasonable number of variables where they all actually add useful value to the model, but not random chance minor correlations.
So to give some like specific examples, so you're saying that R squared is a useful metric for evaluating models, particularly where we don't have some categorical output. So with the cancer detection model, we have this binary classification.
Yes. Then you would
so it's like then you can use accuracy.
Accuracy.
But you could use R squared in those circumstances as well, because can still be an interesting metric because it tells you the proportion of the variance explained in your outcome. So you can use it. That R squared is equivalent to saying, like, if you get an R squared of 0.9, it means that your what you call the independent variables there, the features, the inputs to your model, they together explain 90% of the change in your outcome, which could be in classification could be the cancer, is cancer present or not, or with your energy output example, it's how much energy is the power plant outputting, I guess, is the outcome.
Yes, electrical energy output. Yeah.
Electrical energy output. But yeah, you make a really good point here. The adjusted R squared is critical because let's take that energy output example. If you had 200 possible inputs, independent variables, features that you could be putting into your model, if you just include all those, you'll, like you said, by random chance, you'll probably get an R squared of perfect because there's just so much opportunity for random, meaningless variation to appear to be meaningful. So the adjusted R squared penalizes you for adding more inputs to your model, more independent variables than you need.
That's very cool. Thanks, John. I learned something new today as well about applying R squared to classification problems. That's really cool.
Hey, there you go. It's data science. There's an infinite amount out there.
Yeah,
Yeah, you can never know everything.
absolutely.